Yeah. So classical invariant theory and the three pillars of modern commutative algebra. So in classical invariant theory, the classical invariant theory is a representation theory of the group SL2C in which vector space? The vector space of binary forms. What is the binary form? Binary form is this expression 0.8 that you see here. A naught chi to the power n plus this n choose 1, n choose 2, their convenience. N choose 1, a1 chi to the power n minus 1 eta blah, blah, plus an chi to the power n. It's a homogeneous polynomial of degree n in two variables chi and eta. So now what you do is that, so there's a vector space. Set of all such things forms a vector space. It forms a vector space of dimension n n plus 1, right? Okay, it forms a dimension n plus 1 because it's determined by the n plus 1 tuple of coefficients. Now we can always subject the chi and eta to some SL2C change of variables. So chi eta is basically an SL2C matrix times x1. So chi will be equal to alpha x plus beta y, eta equal to gamma x plus delta y. And let us substitute these values of chi in expression 0.8. You're going to get another expression 0.8 prime. And then the coefficients of the new quadratic form will be capital A0, capital A1, capital AN. So these capital A's will be linear in the little a's. That's absolutely clear. But it's going to be highly non-linear. So capital A1, capital A2, etc. If you write the n plus 1 tuple, that will be a matrix times little a0, little a1, little an, column written column wise. But this matrix, what is this matrix going to be? This matrix is going to be some, let us call this matrix M. This M is going to depend upon this alpha, beta, gamma, delta. Let us call this matrix little g. The group element is always denoted by little g. This capital M of G applied to little a0, little a1, little a. So it's a linear representation of a group. It is a linear representation in the sense that it's a representation of the group as a set of linear transformations. But the matrix, the way the matrix will depend on alpha, beta, gamma, delta is highly non-linear. Okay, so that's what I'm saying. So this matrix I'm going to denote by capital psi G inverse. This is because I want it to become a group homomorphism, not an anti-homomorphism. So capital psi G is an n plus 1 by n plus 1 matrix. And so we got this map little g going to capital psi G inverse. That's a representation. That's a representation of this Lie group SL2C in the vector space, in the finite dimensional vector space V of homogeneous polynomials in two variables. So now, when you have a group representation, and a group acts, when you have a group representation, you want to look at functions defined on the vector space. So defined on the vector space means that you can fix up a basis and you can take coordinates a0, a1, an, and this you want a polynomial. You want a polynomial function from the vector space to C, and you want this polynomial function to be invariant. Invariant means that capital P of psi G inverse of a0, a1, a2 should be the same as capital P of a0, a1, a1. Is invariance clear? 0.9 equation. What yes, invariance means? So it should be invariant, and this should happen for all elements of the group. Now, instead of taking all elements of the group, observe that SL2C is a three-dimensional complex Lie group, and the tangent space is three-dimensional. And so you can take three linearly independent tangent vectors, and you can get the one-parameter group generated by these. So that is the idea. So one of the central problems in late 19th century and early 20th century in algebra was to classify and determine the invariance of this SL2C action. This SL2C action has a habit of popping up at unexpected places. It's one of the most remarkable things about this group SL2C. And So there are various reasons why people will be interested in invariance. So now what happened was that you should look at this lectures on invariant theory by David Hilbert, where this was published in 1898 or something like that, 1896 or something. So classical invariant theory is responsible for creating for constructing three important pillars of modern commutative algebra. That is the Hilbert basis theorem, the Hilbert's Null-Stellensatz, and the Hilbert's syzygy theorem. Let us now, last time we were discussing the invariant, the conjugacy invariance, right? GLN. I asked if you take the set of all matrices M and C, and you look at the conjugacy action. So take a matrix A, take an invertible matrix P, A and P inverse AP. You want invariance. Which functions are invariant with respect to conjugacy? That's another problem. There's another invariant theory problem, right? The trace of a matrix. That's conjugacy invariant. The determinant of a matrix is conjugacy invariant. And last time we discussed that the 2 by 2, sum of the 2 by 2 principal minors, the sum of the 3 by 3 principal minors, the sum of the k by k principal minors, it gives you a list of invariants. Is this clear? Now the next question is that suppose I take a polynomial invariant for the conjugacy action, then that if a polynomial is invariant under conjugacy, that is, if you take a polynomial in the entries of the matrix such that the polynomial evaluated at A is the same as the polynomial evaluated at P inverse AP, then that polynomial can be expressed in terms of these basic building blocks: the trace, the determinant, and the sum of the k by k principal minors. So any polynomial invariant of the conjugacy is a polynomial expression in the basic invariants that we wrote down: the trace, the determinant, the sum of the k by k principal minors. So you say that the sum of the k by k principal minors, well, let k run from 1 to n, that generates the ring of invariants. The ring of invariants is finitely generated, and this is a complete list. What about the case of SL2C invariants? What about this example? In that example, we understand linear algebra tells us that if you take a polynomial which is invariant under conjugacy, then that polynomial must be a polynomial expression in terms of the basic things, sum of the k by k principal minors. Let me give you another example of invariance. Take the group Sn, the symmetric group Sn. The symmetric group Sn can act on the variables, right? Suppose I take a polynomial in x1, x2, xn and take a permutation sigma. Take a permutation sigma and simply replace x1 by x of sigma 1, x2 by x of sigma 2, xn by x of sigma n. So you want p of x1, x2, xn equal to p of x of sigma 1, x of sigma n. That is, you permute the arguments of the polynomial. You think of the polynomial as a function and you're permuting its arguments, and it should remain invariant. What kind of polynomials? Examples, please. x1 plus x2 plus plus xn. Is that correct? x1, x2, xn, the product of all of them. That will not change when you permute the variables, right?
Yes, sir. Yeah.
And then what about x1, x2 plus x1, x3 plus plus xn minus 1 xn? So you take some of the products taken two at a time. That will also be an invariant. So now I've given you another list of n invariants, and the Newton's theorem on symmetric functions says that any symmetric polynomial is a polynomial expression in the elementary symmetric functions. So the ring of invariants there, in that case, is also finitely generated. And I can list the generators. What about this problem? SL2C invariance, this example. What are the polynomial invariants? And is a ring of polynomials, is a ring of invariants, is it finitely generated as a ring? These were the very, very big questions. In fact, Paul Gordon proved that the ring of invariants is finitely generated. It was a constructive proof and a lengthy proof. Later, Hilbert developed his ideas and proved an existence theorem that the ring of invariance is finitely generated. And it is exactly for this purpose that he discovers his Hilbert basis theorem. The Hilbert basis theorem says that if you have a ring of polynomials, take a field K, and take the field of complex numbers if you like. So C of x1, x2, xn. Take an ideal in this ring. Every ideal is finitely generated. It's more is true. It is true in a ring. If the ring is Noetherian, if R is a Noetherian ring, then R, the polynomial ring in one variable, is also a Noetherian ring. That is the modern formulation of the Hilbert basis theorem. Of course, Hilbert described it for polynomial ring of polynomials and ideals in the ring of polynomials. And he uses this to prove that the ring of invariance is finitely generated. Now, Gordon remarked, das ist kein Mathematik, das ist Theologie. That is not mathematics, that is theology, because we are talking about a time when existential theorems were not assimilated in the community the way it is today. For example, today the modern student is perfectly happy to use some axiom of choice, this, that, compactness argument, the solution of the differential equation exists without producing one. So those days were very different. So what constitutes a mathematical proof? That was the philosophy was different quite then at that time. But then so later on, Hilbert discovers what is today known as the Hilbert's Nullstellensatz. I'll describe to you briefly what is a Hilbert's Nullstellensatz. And he uses this Hilbert's Nullstellensatz to explain how you can actually determine the ring of invariance. And then Gordon remarks that theology also has its advantages. So let me explain to you what is a Hilbert's Nullstellensatz. It is one of the most foundational theorems in algebraic geometry. Now, what is Nullstellensatz? Now, let us go back to linear algebra. You've got a system of 5 equations in, say, 8 unknowns. It's not clear, or if or rather, you have a system of 500 equations in 756 unknowns. It is not clear whether this system of equations is going to have a solution, right? What do? You do Gauss elimination. You write the matrix AX equal to B. You take the augmented matrix and you perform a systematic you reduce it to row echelon form, and you do Gauss elimination. And then you say that if the rank of the augmented matrix is larger than the rank of the associated matrix, the system has no solutions. Otherwise, the system has a solution. Now, what is the meaning of saying that the rank of the augmented matrix is larger than the rank of the associated matrix? How will that happen? That will happen if that one way in which that can happen is that you perform row operations on A augmented with B. One of the rows of A became 0, but that row is non-zero in the augmented matrix. See, when you do the row operation on A augmented with B, you end up getting 0, 0, 0, 0, 0, and the last entry in the augmented column, there is a 1 in the augmented column. That would mean that if you take the system of linear equations, call them L1, L2, Lm, Gauss elimination means that if this system has a solution, then I can multiply the first equation by 3 and subtract from the second equation. And I can do these manipulations. I can exchange 2 equations. It's a perfectly valid operation. Or I can add to the third equation 7 times the first equation. By this sequence of manipulations, if you end up with the condition 0x1 plus 0x2 plus ... plus 0xn equal to 1, then you conclude that the system doesn't have a solution. Is that clear? That is Gauss elimination method. That's the essence of Gauss elimination method. Yes or no?
Yes.
Okay. So now, what is given to you? I'm not giving you a system of linear equations, I'm going to give you a system of non-linear equations. f1 of x1, x2, xn is 0. f2 of x1, x2, xn is 0. fm of x1, x2, xn is 0. So these are polynomials. I'm giving you m polynomials in n variables. Now I'm asking you, does this system have a solution? How do you decide whether this system has a solution or not? One way to do it would be the following. You will go back to your high school algebra and you will ask, when would two quadratic equations have a common solution? Or when will two polynomials in one variable have a solution? You will then there is a very systematic way. You take a polynomial, you take two polynomials in one variable, and these two polynomials in one variable have a common root if the so-called resultant is 0. The resultant is a polynomial expression in the coefficients of the coefficients of the original polynomials. Then you do the same thing. You are looking at f1 of x1, x2, xn is 0. f2 of x1, x2, xn is 0. Now, this complete list has a common solution means that the first two must have a common solution. That means that I can think of the first two as polynomials in x1 whose coefficients are polynomials in x2, x1, x2 up to xn minus 1. Is that clear? So what I will do is that I will take the resultant of the first two polynomials with respect to xn, and that resultant should be 0. That's a condition. Now that resultant can actually be written as a linear combination of the original two polynomials, except that these linear combinations will be polynomial expressions in the coefficients. In other words, the resultant of the first two polynomials will be in the ideal generated by the polynomials. Similarly, I take the resultant of the first and the third. I take the resultant of fi and fj, call it rij. And this resultant can be written as lies in the ideal generated by f1, f2. Now these resultants, this family of resultants must have a common root. But the advantage of, you will say, okay, from one system of m equations, I got m into m minus 1 by 2 equations. I got a bigger system. But we got an advantage. This new system doesn't involve xn. The variable xn has been eliminated. Now I will do the same thing. I will keep on eliminating the variables systematically one by one. And I'll get newer and newer systems of resultants. The more efficient way to do it would be to call resultant ideals. Don't work with the polynomials themselves. Instead of working with f1, f2, fm, you along with f1, f2, fm, you also include all linear combinations. No? Summation lambda j fj, where lambda j's are polynomials. Because if f1, f2, fm have a common root, then that same common root will also be a root of summation lambda j a fj. No problem. So instead of working with a list of polynomials, you look at the ideal generated by the polynomials. And now these resultants, look at the ideal generated by these resultants. So you talk about the resultant ideals. The first resultant ideal is now doesn't involve is generated by a system of polynomials not involving xn, and you keep doing this again and again and again, and you would have systematically eliminated all of them. But in the process, if some linear combination of these resultants happens to be a non-zero constant, then you're sunk. Because what is the condition? These resultants must have a common 0. But if the resultant must have a common 0, then the linear combination cannot become 0. Must remain 0, right? And the linear combination becomes a non-zero business, then you are in trouble. So the condition is that, so the necessary and sufficient condition that the system of polynomials f1, f2, fm must have a common root is that the ideal generated by these polynomials mustn't contain 1. It's a So in one direction, the result is trivial, because if 1 is the ideal generated by them, then these polynomials will not have a common root. The converse, which we can prove using the theory of resultants and elimination theory. Now this is the Null-Stellensatz zero position theorem. So it gives you a necessary and sufficient condition for a system of polynomials to have a common root. So Hilbert uses this to come up with an algorithm to generate a complete system of invariants. All these things are discussed in his lectures on invariant theory, in classical invariant theory. Another thing that happens is that you have these invariants. Now, when you have these invariants, usually there will be several invariants. There will be invariant of order 4, there could be an invariant of order 8, there could be an invariant of order 12, there could be an invariant of order 20. But so you got first invariant is I1, say I4, an invariant of order of degree 4, I8, invariant of degree 8, I12, invariant of degree 12, I20, invariant of degree 20. Polynomials. There are polynomials in A0, A1, an. Now, it may happen that these polynomials may not be independent. There could be a relation between these polynomials. For example, what do you mean by relation? Take, for example, the polynomials UV, VW, UW, UVW. I've given you 4 polynomials. None of the polynomials can be expressed as a polynomial in the other 3. You can't express UVW in terms of UV, VW, and UW. But UVW squared is basically UV, VW, UW. But then I can get UVW the whole squared, but I can't get UVW. I can't take the square roots. No? I want a polynomial expression, not some general function. So we say that there's a non-trivial relation between these 4 polynomials. And these kinds of relations. So now there could be several relations between a given set of polynomials. And there could be relations among the relations, and so on. These are called a relation between invariants is called a syzygy. And there could be several relations. And there could be relations between the relations. There could be second order syzygies, third order syzygies. But this chain of syzygies stabilizes. That is the Hilbert syzygy theorem. So these 3 theorems are extremely important. In fact, the Hilbert syzygy theorem, etc., all these things are extremely useful when you study several complex variables. For example, if you look at Gunning's second volume, Holomorphic Functions of Several Complex Variables, the local theory, he discusses these things, the Null-Stellensatz, the syzygy theorem, etc., from the point of view of local theory of analytic functions of several complex variables. So even from our complex analysis perspective or the complex geometry perspectives, this is not completely devoid of interest. So now let us go a little further using calculus to determine invariants. Now let us go back to the same classical problem of trying to find all polynomials which satisfy this equation 0.9. Now this matrix A comes from this capital A, not capital A1, etc., are coming from this little g. I mean, it's a matrix applied to the little a naught, little a1, little an, and the matrix is non-linear in little g. So I will, as a choice, I will take alpha, beta, gamma, delta to be 1, t, 0, 1, upper triangular matrix. And I can allow the t to vary as a 1 parameter. So what happens is that, so now in this equation 0.9, the t is appearing on the right, but the t is not appearing on the left. So differentiate 0.9, the left hand side becomes 0. Use chain rule to differentiate the right hand side, and you see what happens. And you put t equal to 0. You do the differentiation and you put t equal to 0. You're going to get a first order partial differential equation for p. And that first order partial differential equation is basically 0.10 prime. Now that is not the only thing you can do, right? You can take the lower triangular matrix 10T1 and you can carry out the same program. You will get another partial differential equation 0.10 double prime. That is an exercise. What is that other one? There is a third one, right? I can take e to the power t 0, 0 e to the power minus t. That's also an element in SL2C. I can do the same thing and get one more partial differential equation. This last one is very easy to deal with. And so these are called infinitesimal generators for the Lie algebra of. So I got three first order partial differential operators. There are three vector fields, right? And I can take the Lie bracket of these vector fields, and you're essentially going to get, you will realize that the three bracket relations you get with x1, x2, x3 are the defining equations for the Lie algebra little SL2C actually. So in other words, what we have done is that we have passed on from the action of the Lie group, which is highly nonlinear, to its linearization and the action of the Lie algebra, which is linear. So this idea of linearization, which is so common in dynamical system, where the nonlinear problem is approximated by linear problem. In the context of Lie groups, we have an advantage that because of the presence of the group structure, one recovers practically the full information about the nonlinear action from the study of the linearization. Whereas in general theory in dynamical system, only the local behavior of the nonlinear system is reflected by the linearization. But because the Lie group structure, we can do much better. Let us put this all in the abstract framework. Let G be a Lie group and A be the Lie algebra. That is the tangent space to the group identity, and the Lie algebra of G. So for a little G, let us take the inner automorphism generated by this G. And this inner automorphism is a diffeomorphism. Because the diffeomorphism, I can differentiate it with respect to x at 1, and I'm going to get a invertible linear transformation from the Lie algebra to the Lie algebra. A Lie algebra is first and foremost a vector space. So you got an invertible map from linear transformation from A to A. So in other words, this map G, little g going to the derivative at 1 is a map. It takes, and little g comes from the Lie group, and the derivative is a invertible linear map from A to A. Invertible linear map from A to A means it is an element of GLA. And that's a group representation. So you represented the Lie group. So you got a representation of a Lie group in the vectors in the Lie algebra. And this representation is called the adjoint representation, capital add G. So now this is adjoint representation. One can go a little further, and one can now G is a Lie group. GLA is also a Lie group, and so I got a group homomorphism from one Lie group to another Lie group. So I can differentiate this group homomorphism itself at 1, and I'll get a linear map from the Lie algebra A to the Lie algebra of this Lie group. The Lie algebra of this Lie group is endomorphisms of A, and that is called the little add. Okay, so we will these things are described in Brian Hall's book, if you like. And then we talked about conjugacy, and we talked about the invariants under conjugacy, which are the class functions. So I asked you to provide a list of n invariant. We already have that. Some of the k by k principal minors. The subject of representation theory of groups is too vast for any attempt at surveying it in an introductory chapter. What we have done here is a glimpse of what to expect and the texture of mathematics that its study entails. It should be clear that the subject would borrow ideas from many parts of mathematics, algebra, topology, and analysis. In particular, which is indeed the most attractive feature of representation theory. It does return back rich dividends. And now we'll discuss a few words about the books on representation theory. There is this book by Walter Lederman, Theory of Group Characters. This is a very old book, but a very beautifully written book actually. It is lucid, but he uses the complete throughout the book, he describes representation theory in terms of matrices. He doesn't use any calculus. He uses just linear algebra and group theory, and he covers a substantial amount of material. And there's this book by Steinberg. It's a very basic book and well suited for a beginner with applications and illustrated with lots of worked examples. Of course, the scope is somewhat limited. He proves the Burnside's PQ theorem, for example. He proves the dimension theorem. He gives applications. There is a chapter on Fourier analysis on finite groups, and so on. Of course, certain things are omitted. For example, tensor product representations are omitted. Then we have got this book by Barry Simon. Barry Simon is an analyst and is a very powerful analyst and a world-renowned analyst. And so here we see an introduction to an algebraic subject from the analyst's perspective, but you begin to feel a certain slant towards harmonic analysis, which is natural. In fact, the later parts of the book, he does talk about the Peter-Weyl theorem and other things. But the great thing about Barry Simon's book is that the algebraic aspects are well developed. For example, there is a chapter on Young tableau, which is a chapter in combinatorics, for instance. Then there is a page which is missing. So let me just look at this missing page. And let's see. I'll have to open my Gmail. I sent it to Krishna. Just a minute. Let it open. Missing page. Can you see it?
Yes.
Yeah. Also, the book of Barry Simon also uses a little bit of algebraic topology, such as the higher homotopy, the long exact sequence in fibrations and thoughts. Towards the end, he uses a little bit of that, not much. And there's this book by E. Winberg. This book treats in detail the theory of orthogonal and unitary groups in the light of special functions, which I talked about. And then there's this book by Brian Hall, an admirable and delightful introduction to Lie groups and Lie algebras, covers a substantial ground, and it's aimed at undergraduates. And then there is this list of general references. There is this book of Apostol, which I mentioned, the book and the paper of Duke and Spears on the generalization of the Gauss's law of quadratic reciprocity against the representation theoretic character theory. And then there is Hawkins' paper in the Archive of the History of Exact Sciences about the correspondence between Frobenius and Dedekind. Then we talked about Hilbert's lectures on invariant theory, T.Y. Lamb's article in the notices of the IMS, Lederman's book. We talked about Miller's book on Lie groups and how representation theory is explained in the light of special functions. G.W. Mackey's book contains 31 beautiful essays on the interconnections between representation theory and physics, probability, and number theory. And then there's this paper of Monson, the web draft, on finite Fourier analysis and Dirichlet's theorem. And so this completes the 0th chapter. And let us just not start the new chapter today. Let us just take stock of the situation. The first chapter basically talks about the most basic notions of representation theory, the definition, and then the trivial representation, the sign representation. The equilateral triangle gives you the symmetric group on 3 letters are the symmetries of the equilateral triangle. So straight away the group itself is realized as a group of matrices, and then the dihedral group, the group of rotations of the group of symmetries of the regular polygon of n sides. Then there is an interesting representation of S4. Directly you can take A to be omega 0 minus omega squared 1 and B to be 1 omega squared 0 omega, where omega is a cube root of unity. You can check that if you take A squared, A cube, etc., and B squared, B cube, and A, B, A, and all that kind of stuff, you're going to generate 24 elements and no more. And these 24 elements are going to be precisely S4. And so you get a straight away by serendipity, we get a two-dimensional representation of S4. But somebody gave us these two matrices. How would you have divined that this would work, that this kind of stuff would work? And the Taylor and Lehrer in their book on unitary reflections explain how this can be arrived at systematically by an algorithm called the Shepard-Todd algorithm. Then you got this group Sn, the symmetric group. You got the sign representation, and then of course you got the trivial. Always you got the trivial representation. Everything going to one. The G to C star, the trivial group homomorphism. Here you got a non-trivial one. G going to C star, the permutation going to the sign of the permutation. So for S3 we have got a set of 3 representations, and for Sn we will have as many as there are partitions of n. That is a number of set of conjugacy classes. Then when our two representations are equivalent, if one of them can be obtained from the other by conjugating by a fixed matrix T. In other words, all these matrices, this matrix T conjugates all the phi g's to psi g's simultaneously. And then these T's are called intertwiners. And some examples of intertwiners: the standard representation of Sn. Each element of Sn is a permutation. Now you start with the identity matrix and apply the same permutation to the columns. So start with In, take a permutation sigma, and permute the columns of In. You get a matrix A sigma. This map sigma going to A sigma gives you a representation of Sn. This is called the standard representation. But this standard representation will have the property that all these matrices A sigma. See, when you take an identity matrix and you permute the columns, no matter how you permute the columns, every row must have one in exactly one place at one of the positions in every row. So the column vector 1 1 1 1 1 will be a common eigenvector for all of them. And so this representation will split, and then you can take the ortho complement. The ortho complement will also be a representation, and that's the representation that we'll work with. Then we talk about invariant subspaces, G invariant subspaces, and stuff like that. So I think we will start this some other time. When is some other time? And then we could talk about two notions of indecomposability and irreducibility. Fortunately, they'll be one and the same. When the group is compact or finite, they will be the same notions. We are not going to be discussing non-compact groups at all. One example where indecomposable and irreducible are quite different, and that's a non-compact group, Z. Then there is the notion of unitary representations. So a representation is a map from G to GLV. Now if V is a complex vector space endowed with a Hermitian form, then instead of working with general GLV, I can ask whether I can work with unitary operators. In fact, if G is a finite group or a compact group, every representation is equivalent to a unitary representation. That is Maschke's theorem. And so you can actually, and you can use this unitary argument to prove that every representation will decompose into a direct sum of irreducibles. And we're going to prove later that that's going to be unique. And that is what its complete reducibility, Maschke's theorem. And then we'll prove all these things, and then that will be the first chapter. And what about abelian groups? For abelian groups, nothing interesting happens. If you take a general representation, it will decompose into a direct sum of irreducible representations, which are all have dimension 1. So that's why the dimension 1 representation, the characters as we described it right at the beginning, they are the only interesting ones. And then there is I inserted here a Fugler-Putnam theorem. We will discuss this later. And then some more examples from Steinberg's book, conjugate and contragradient representation, new representations from old, etc. So we will discuss these things. The non-trivial part here is a complete discussion of the dihedral group, determining all the representations of the dihedral group of order 10. In this chapter, this is a notorious example. because it is forcing you to do some work, and we are going to anticipate what is to come. And so if you see what happens is that how many irreducible representations will be there. Suppose there are k irreducible representations, degree 1, degree 2, degree k. Then the sum of the squares of these degrees must be the order of the group. So here the order of the group is 10. So how do you write 10 as a sum of squares? One way to do it would be one way to do it, and how many such summands will be there? The number of summands will be the number of conjugacy classes. So we should find out how many conjugacy classes are there in the dihedral group, for example. So these are some of the kind of questions that we should be looking at actually. So this formula, order of G is d1 squared plus d2 squared plus da plus dk squared. I call it the Parseval formula. Do you see the remarkable similarity with Parseval formula? Mod integral 1 upon 2 pi I integral mod f squared equal to a naught squared plus 1/2 summation mod a n squared plus mod b n squared for Fourier series. It is an energy. It's some kind of an energy equation.
Yes.
So this is like an energy equation actually. So and then that we can predict the number of irreducible representations, etc. So let's stop here and let's continue this later. So you got a glimpse of what is to